right, in this video we're going to talk about the integration technique called integration by parts. So in general, what we want to do, talk about a little bit first is how do I integrate products of functions? So how do I integrate functions that look like this, where they've been built by taking one function and multiplying it by another? All right, and unfortunately there is no product rule for indefinite integrals. So unlike with derivatives, right, if I have a function that is a product of two functions, the product rule will handle taking the derivative of that, as long as I know how to take the derivatives of each of the individual parts. But there is nothing, no single rule like that for indefinite integrals that we're about to talk about. So let's just take a look at a couple of examples before we actually get to the integration by parts to kind of illustrate what I'm talking about. So first off, at this point you should have already talked about substitution and learned about substitution. And so some products of functions can be integrated just using plain substitution. So an example of this would be the integral of x times e to the x squared. Okay, so that is the product of this function x here and this exponential function over here. Okay. All right, and so what I would do is to choose u, and in this case I could choose u to be x squared, right? And then calculate my du, right? So excuse me. So my du will be, the derivative of u will be 1, then tack on the du. The derivative of x squared is 2x dx. Okay, and then when I go to make my substitution, I notice, well, I have this x and this dx here, and so I don't have the 2, but that's an easy fix because I can just multiply both sides by 1/2. So multiplying this equation by 1/2 gives me this, and now everything's lined up for the substitution. If I have x e to the x squared, right, substituting the u for x squared, that will give me that e to the u, and then the x and the dx combined, right, that substitutes to 1/2 du. Okay, so I switched every single occurrence of x over to u's, and now I just need to integrate that function, and the first thing I'm going to do is pull that 1/2 out. That's a constant, so the constant multiple rule says just rewrite that constant and then multiply by the antiderivative or indefinite integral of this function. And integrating this function is easy, right? E to the x is its own derivative, so it's its own antiderivative. So I get 1/2 times e to the u plus some constant c. So there we, one last step, right? Almost forgot. We have to back substitute, right, to get back to the original variable here, x. So when I back substitute, u is x squared, so I just put that right in here. And so I get 1/2 e to the x squared plus c as the antiderivative, or indefinite integral of x e to the x squared. Okay, so that substitution took care of that product right there. But the problem is that other products can't be integrated using substitution. So it's not like substitution will take care of every one that we will do. And so an example of that would be this one right here, x e to the x. And notice that the only real difference from the last one was that I had x squared up on top as the exponent for the exponential function. And the derivative of x squared was 2 to the x, almost this function out here, but now that's just not true anymore. So that's going to kind of complicate things. Even though the first example that we did looked, actually looks a little bit more complicated than the one we've got here, it just turns out that that the fact that the exponent's derivative was a factor in here just kind of made things easier. And now the derivative of the exponent is just 1, so I kind of have this extra x in here that kind of complicates things. So it may be a little difficult to kind of look at that and say, hey, how do I know that no substitution will work here? And the best way to do that is to just try it, and you'll kind of find all the mistakes that you could make, and there's no shame in making those mistakes, you know, because that's how you learn, you know, what works and what doesn't work. But if you make a mistake, then the main thing is just don't give up. Is try something else and see if you can figure out how it works. And if you can't figure it out after trying a few things, then it kind of probably means that there's probably some other technique that you need to try. So let's just go ahead and go down that path really quickly. I don't want to take up too much time in this video, but there's no obvious substitution that seems to work for this integral. So if I try u equals x, well, first off, that's never a good choice, right? For u equals x, that gives you a du equals dx, and then when you substitute, you get u e to the u du. So if you look at it, that's really not going to help you. It's not any simpler than what you started with. In fact, really all you did was change every x over to a u. It doesn't help you, right? The goal of substitution is when you substitute, you should wind up with a simpler integral than you started for. And so that's just never a good choice. If you can do this one, well, you could have done it without doing that work. So that's never a good choice. All right, the other thing that you might try is, how about everything? What if u is x e to the x? And you can see what happens here is that you get kind of a complicated du, right? When I go to take the derivative over here, I have to use the product rule, right, to take that derivative. So using the product rule, I would take the derivative of x and get 1, and then I would leave e to the x alone. That's how I get this e to the x right here. Then the product rule says put a plus, which I'd put right here. And now the product rule says the function that you took the derivative of the first time, x, you leave it alone. So that's why I have that x right here. And the function that you left alone the first time, e to the x, now take its derivative. Well, the derivative of e to the x is e to the x. So that's how I get this e to the x right here. So you can see I have a complicated du here, and that's just not usually very helpful at all. You can see I do have some parts that are in here, this x e to the x, but the question is, what do I do with this thing, this extra e to the x? How do I account for that? Remember, every single occurrence of x will have to be converted over to some occurrence of u using these two equations right here, and so that just turns out to be kind of difficult. You actually can force this to work with a little trick, but I'm not going to go over exactly the details of it, but the little trick is to add e to the x and subtract e to the x out of here, and it turns out that you can kind of finagle this around and make it work, but really kind of what I want you to take home from here is that choosing u to be everything in your integrand, right, that's not usually a good choice. Okay, so that doesn't really seem to work out. It kind of does, but it's really kind of tricky. So the next obvious thing is, how about just e to the x? Okay, and so if I choose u equals e to the x, I get du equals e to the x dx. So far that's looking pretty good. That's not very complicated, and that stuff does appear in my integral here. So that e to the x dx, right, that is all taken care of. That's all going to be switched over to du, right? So that would only leave this x to account for. So how am I going to do that? Well, what you can do is solve this original substitution, u equals e to the x for x, right, by taking the natural log of both sides, right? On the left side, I'll get ln u. On the right side, I'll get ln of e to the x, which is just x, okay? And so x equals ln u. I'll substitute ln u in for x and get this, and I'll substitute for e to the x dx, I'll get du. Right? So that gives me this integral, the natural log of u du. So the question is, well, how do I integrate that? And we haven't learned how to do that yet because it takes integration by parts. Okay, so that substitution does lead to something that could possibly work out, right? But in the end, it requires another technique, right, beyond substitution. So none of the obvious things here really work. Okay, so that leads us to something that will work, and that is a brand new technique, right, to us learning Cal 2, and that is integration by parts. And so integration by parts is a method used to integrate some products of functions when substitution will not work. It's not guaranteed to work every single time, and so sometimes it won't work. But it allows us to integrate products that we couldn't do by substitution. All right, so there is a formula for integration by parts. The integral of u dv equals uv minus the integral of v du. So where does that formula come from? It actually comes from the product rule for derivatives. If you kind of rearrange it around a little bit, and that's what you will get. So I'm not in this video. I'm not going to go over exactly how you would come up with that formula. I'll do that in another video later on. So in this video, I'm just going to kind of show you how you would use this formula to do integration by parts. Okay, so here we are. This is the example that we looked at before, x e to the x. We tried some of the obvious substitutions. Nothing really panned out, right? So what we're going to do is use integration by parts. To do integration by parts, you're going to pick two parts of your integral and label one u and the other dv. Okay, so in substitution, you only use the u. In integration by parts, we're going to add an extra thing inside here. Now, one of the requirements for u and dv is that when you multiply them together, it has to come out to be the entire integrand. In other words, all of this stuff inside here. You can't leave parts out, right? Between u and dv, when you multiply those two together, right, it has to be the entire integral that you started with. So it turns out in this example, the best choices are u equals x, right, and dv equals x dx. So first off, let's verify when I multiply u and dv together, right, that would be x times e to the x dx. And notice that would be all of this stuff right here. It has to be that way, okay? You can't leave out stuff. Whatever you pick to be u, right, and whatever you pick to be dv, right, when you multiply those two things together, it must come out to be the entire integrand, okay? So you probably have, at this point, a lot of choices. How did you come up with u equals x and dv equals e to the x dx? All right, does it really matter how I pick those? Could I reverse those, right? And it does turn out that some choices are better than others, okay? And we'll talk about that after we finish this example, okay? So for right now, we're going with u equals x and dv equals e to the x dx. We've chosen u. We've chosen dv. We've verified that when we multiply u and dv together, we get the entire integrand up there. So now what do you do? Well, just like in substitution, right, you're going to calculate du. And that part's almost exactly the same, right? We chose u equals x, so we're going to take the derivative, right? The derivative of u is 1 times du. The derivative of x is 1 times dx. So we get du equals dx. All right, and this is the new part, right? Remember, we chose dv. We're going to calculate v by taking not the derivative, but the antiderivative of dv. Okay? So remember, we chose dv to be e to the x dx. So what we're going to do is integrate this part here and go back to v. So we're kind of going backwards of what we normally do here. And the antiderivative of e to the x is e to the x. So going backwards here, we start with dv, we integrate that, we'll get v. We integrate e to the x, we will get e to the x here. And don't worry about the plus c, right? Just make sure at the very end, when you get done doing this, that you put the plus c on at the end, and you're good. Okay? So calculate u, calculate v, or du and v. And then we will apply the formula for integration by parts. So you remember where I told you about the formula for integration by parts. The integral of u dv is uv minus the integral of v du, right? And now we have all of the parts to that. We know u is x, we know du is dx, we know dv is e to the x dx, we know that v is e to the x. So what we're going to do is just substitute those things in to the formula for integration by parts, and that's what we would get. U, right, is x, so that's where this x comes from. dv is e to the x dx, so that's where this comes from, equals u is x, v is e to the x, okay, minus the integral of v, all right, v is e to the x, and that's du. du is equal to dx there, okay. So that's what we wind up with in the formula for integration by parts. The only thing is that we have this integral still left to do. And so integration by parts kind of does depend on you being able to do this integral right here. If you do integration by parts and then you wind up with something here that you can't deal with, then integration by parts might not be the right technique. Remember, it doesn't work for every single product. So. All right, so now all we have to do to finish this up is to compute that remaining integral, and the integral of e to the x, right, that's a real simple one. The integral of e to the x is just e to the x, so this entire integral gets replaced with e to the x, and then don't forget to tack on the plus c at the end, okay? And so that's it for this first example of integration by parts. The integral, right, the original integral, x e to the x dx, comes out to be x e to the x minus e to the x plus some constant c. Okay. Now, the last thing in this video is guidelines for choosing u. And now you may say, well, wait a second, what about dv? Well, remember the requirements for u and dv is that when you multiply them together, then it has to be the entire integral. So whatever you choose to be u, that kind of narrows down what dv is going to be. So these guidelines are called the LIAT guidelines, however you want to say that, right? And so the LIAT stuff there just stands for logarithm, inverse trigonometric, algebraic, trigonometric, and exponential. So in general, what you want to do is to choose u to be the function that comes first in this list. So logarithms, if there's any logarithms, you want to choose those to be u, right? Or if there's no logarithms, then inverse trigonometric functions. Then algebraic functions, then trigonometric functions, and then exponential functions. You do have to be careful. These are only guidelines, right? They don't always work. Again, there are some exceptions, but in general, these guidelines are pretty helpful, especially for kind of book problems that you do. In the example that we did, we had x, which is an algebraic function. Remember, that includes power functions and polynomials, and rational functions and general algebraic functions, right? So that's what we had. X fell into this category. And then we had exponential function, e to the x, right? That's what that one was. So we chose u to be the algebraic function, right, first. And so then that kind of really forced the dv to be e to the x dx, okay? So those are the general guidelines for choosing u. In the following videos, we'll just be taking a look at some more examples of how to use integration by parts.